let's do that. Hopefully you can all see my screen there. Cornelia, thanks for the introduction. Yeah, it's really good to be here. I hope everyone is, staying safe. Before we get started, if anyone has any questions, just post them in the Zoom chat and I'll be sure to check them and get back to you on those. If something comes to you, later after this meetup, feel free to reach out on LinkedIn or Twitter or something and we can chat about anything that you might have questions about. So yeah, I'm really excited to be here and to talk to you all about something that we've been up to recently. And so just a quick outline for what we'll talk about today. We'll start by outlining a maturity model for conversational AI. Not all bots are created equal, right? There are simple chatbots, and then there are sophisticated AI assistants or contextual assistants that leverage some of the concepts that we'll talk about today. So we'll do that first. And then we'll talk about some of the components that you need to build these robust contextual assistants. You need good research and machine learning. You need engineering best practices. You need training data. And of course, you need continuous learning cycles. So we will walk through the research portion of it, which is the transformer-based architecture for NLU, which is diet, or dual intent and entity transformer. And we'll also talk about transformer-based architecture for dialogue called TED, which is the transformer embedding policy. And then we'll talk about how these are available in developer-friendly workflows so we can empower everyone to create great AI assistants. And a little bit about Rasa. Rasa is building the standard infrastructure layer for conversational AI. So our mission here is to empower everyone, citizen developers, and all makers to build AI assistants. We strongly believe that you don't have to be a machine learning researcher to be able to build AI assistants. So we've been trying to sort of democratize conversational AI. And the way that you do it is with building tools that are free and open source, and we champion other open source tools as well. We also focus on the developer community and do a lot of research on natural language processing and natural language understanding and ship applied research to solve these problems. Was just looking at some of the questions there, but I'll take a look at those after the meetup. So conversational AI, I think like Cornelia said, is not a new concept by any means. It's actually been around since the 1960s when MIT released the first ELIZA bot, which was an open domain system, right? Meaning that it can talk about anything that the user wants to talk about. So it's not new by any means, but for a few years now, and especially since 2016, it started experiencing a renewed interest and focus. And if you've talked to chatbots, especially in 2016, and for the following couple of years, you'll notice that that wasn't the case, right? That AI assistants weren't that intuitive or intelligent or capable of understanding natural language in a way that we do, even in narrow domains. So it's sort of what you see here on my screen, where you interact with an assistant and you ask it a question and it answers, but you ask a follow-up question or you digress or engage in conversation that doesn't follow an if-else condition or doesn't follow conditional logic, and it immediately fails. So the problem that we're trying to solve today is how can you move beyond if-else statements and rules and get rid of state machines and really use machine learning and data to create truly contextual assistance. Right, so what do we mean by contextual assistance, and are all assistants created equal? And the short answer is no. There are many levels of AI assistants, and their maturity model can actually be defined by their capabilities. So let's walk through that now. At level 1, you have notification assistants. It's a traditional notification assistant that can send you notifications or reminders about events and things in which you've explicitly expressed interest. For instance, think of like push notifications, think of a pizza delivery bot letting you know that your order is on its way or something like that. It's 100% driven by rules and if-else statements, and there's no machine learning at this point. At level 2, you have a basic FAQ assistant. You can ask the assistant a simple question and expect a pre-built response. It can even handle some basic back and forth and dialogue, but everything here is still rule-based and powered by if-else statements or state machines. At this point, though, intent identification and entity recognition happens, but the dialogue management portion of it is not powered by machine learning. And this is the most common type of assistant that we see today. At level 3, the assistant is able to understand context or what the user has said before, when, where, and how they said it. You know, for example, if you're building a financial assistant, the word bank here means financial institution and not a riverbank. You know, the word balance means cash balance or account balance, and not the balance of things or neutrality. So context, right, of course, matters. Level 3 assistants are also capable of understanding and responding to different user inputs and unpredicted user behavior. So human language is incredibly messy and unpredictable. If you're building a weather assistant, which can be a very simple assistant, all it has to do is tell you what the weather is going to be like by calling an API. There's 40,000 different ways you can ask about the weather, right? So it may not be possible to input all 40,000 different utterances or input all 40,000 different ways a conversation could go. That's simply not scalable. But you still want to account for such complexity. And you do that with machine learning policies that can learn from existing examples and generalize based on those examples. At this level, the assistant also learns from previous conversations and it improves over time. So level 3 assistants are possible today, and you can use open source technology to build level 3 assistants. At level 4, the assistant gets to know you over time, and as a result is super personalized to you and your use case. That's typically what a level 2 assistant can, 4 assistant can do. And at level 5, right, the assistant is even more advanced. It can not only do everything that a level 4 assistant can do, but it can also run entire parts of a company's operations, like lead generation, sales, HR, or finance. And it can also run and delegate a host of other autonomous assistants. Both of these assistants are not possible today, but you know, we might be able to get there in a few years. So as you saw, conversational AI is not solved, far from it. Conversational AI is also not easy. It's actually a really hard problem to solve. And this is a great image of something that, you know, looks like an airplane, and I can't take credit for it. Actually, Francois Chalet tweeted it a while ago. So I grabbed it from his tweet, and he said, you know, if something looks like an airplane, but doesn't fulfill the function of an airplane, which is to fly, then this thing here that you see on my screen is not truly an airplane, right? It just looks like it. And so if something mimics natural language and it just does statistical and language mimicry without understanding language, then that something is not truly natural language understanding. It's just something that seems like it. So level 3 assistants, you know, are hard, but we can get there. And we are building those level 3 contextual assistants. So one of the components that you need to build these successful assistants are great research and machine learning. And the past 2 years have been really amazing for NLP. The past 18 months especially has been great, right? We saw Google's BERT, which is an NLP pre-training technique released by Google. One of the cool things about BERT is its ability to pre-train bidirectional contextual language representations models on a large text corpus. And as a result, the pre-trained BERT model can be fine-tuned with just one additional output layer to create state-of-the-art models for a wide range of NLP tasks like question answering, language inference, named entity recognition and you don't need any task-specific architecture modifications to do something like this. Okay, can you share an opinion regarding chatbots built on various cloud providers? You know, the Zoom chat thing was popping up, and I thought I could just take a look at these questions here and try to make it a little bit more interactive by looking at these questions as we're doing this, because if we were doing an in-person meetup, I know that we would have taken questions, you know, during the talk. Right, we can probably chat about that later for sure, but let me just like jump right into the research that open source conversational AI technology uses. So BERT was great, and so did other large-scale pre-trained language models. They allowed us to create better applications with better representation and accuracy. And large-scale pre-trained language models have always shown promising results on natural language understanding benchmarks like GLUE and SuperGLUE. And since these embeddings are typically well-equipped to generalize across tasks, they've been used a lot. But one of the drawbacks with this is that they're very computationally expensive. And so here's what happens with conversational AI and dialogue systems, right? There are two components to this that we want to talk about. The first, the way that we approach it is that we have two components. The most important piece here is, the first part is NLU, and the second part is dialogue management. And the goal of NLU is to extract structured information from messages. And the most important parts of any message are the intents and entities. So if you wanted to say something to your assistant like, how much money did I spend at Starbucks last week, or something like that, your intention here is to search your transactions. And the key piece of information here is, the vendor Starbucks, because that's the transaction you want to search for. So that's the NLU piece of it. And the second piece of it is dialogue management, which is you run the NLU component to identify the intents and extract the entities. Dialogue management decides what to do next. So it looks at the user's previous state using the state tracker, and it predicts the next best action the bot should take. So looking at everything that's been said before and looking at everything the user has just said or asked, what's the next action that I can take, right? It could be sending a message back to the user or calling a REST API, querying a database, and then sending a response and so on. But that's the dialogue management piece of it. And you need good research to solve both of these aspects and to do better with both of these aspects. And so the next action prediction happens by machine learning policies and the training data that we have in place. And the state of the tracker is determined by previous events, including information from NLU and previous actions. And once an action gets executed, that action gets added back to the tracker, and the tracker gets updated each time there's a user message. So this happens in a loop, and the loop is essentially a conversation with the user. So we released a new multitask transformer architecture for this. It's called DIET, or Dual Intent and Entity Transformer. It's a neural network architecture that does intent classification and entity extraction together. So it consumes one message and spits out the intents and entities at the same time. So one model that does both things. And it can use any pre-trained language model in a plug-and-play fashion. You can use BERT, you can use Glove, Convert, and so on. And in our experiments, there wasn't a single set of embeddings that was consistently best or better across different data sets. So we thought having a modular architecture was super important. And one of the reasons we also wanted to have a modular architecture is that those typically fit into a software development workflow. And that's important because we want to encourage citizen developers and everyone interested in building conversational AI assistants to make use of this latest research. So we can go into detail about this, and I'll just do a quick summary. This diagram, by the way, is based on an academic paper that we're about to make public soon. So as soon as it's public, I'm happy to share that with you. So basically how this happens is, previously we said, let's say you're asking your assistant how much money you spend at Starbucks, right? In this academic paper, the example that we wanted to use was, I want to play ping pong. So the intent, as you can guess here, is to play a game. And the entity, as you can guess, is to play ping pong. Like, that's the name of the game. So how this happens is raw text is split into tokens, as you can see. And in the simplest case, it's just splitting that sentence up into words with white spaces. And the words are then represented numerically with vectors and then processed even further by identifying the intent and entities. So let's take a look at the pre-trained path here that you see on my screen, the pre-trained embedding. The token gets fed into the algorithm. It is then represented numerically with vectors. And you can plug and play any pre-trained model here. So as you can see, you can use BERT, you can use Glove, you can use any other model, Convert, and plug that in and give it a go. And that happens at all of these places that you see the pre-trained embedding here, 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 and here. So on the other side here, you'll notice that we are generating sparse features from the tokens. So think of this as a one-hot encoding of the word. And we also take character engrams. And then this is passed to a feed-forward layer. First, everything is concatenated and processed in a feed-forward fashion. Then the output from the pre-trained path here is concatenated once more, and the concatenated output from the sparse features here is concatenated once more and inserted into another feed-forward layer. And let's take a minute here to look at all of these feed-forward layers that you see on my screen in this diagram. All of these are just, they're all sparse, they're not dense layers. The reason being, we wanted to keep it lightweight. So dense layers are often pruned after the fact to make them lightweight. And all of the feed-forward layers here in DIET are sparse from the get-go. We wanted to keep it lightweight, and one of the reasons for that is that lightweight models tend to be more conducive to AI assistance and conversational AI. So after this processing occurs, where these tokens get split, they're represented numerically, they're processed in the feed-forward fashion. This processing occurs, this result here is a vector, and then that's passed into the transformer layer. And a sequence of entity labels gets predicted through a CRF or a conditional random field tagging layer that's on top of this transformer output sequence that corresponds with the input sequence. And for the intent labels, the transformer output for the classifier token and the intent labels are embedded into one single semantic vector space. So here's how you can use diet in your Rasa project or in your model. This is an example configuration file that you see, a config YAML file. That's where you define and set your NLU pipeline and policies. And the pipeline files typically defines your NLU, and the policy file, which we'll talk about in a little bit, defines dialogue management. So before the diet model, you can specify any feature you want to use. We used the convert featureizer. You need a tokenizer, because these models don't split on whole words. They have embeddings for subwords and pieces of words. So you need a specific tokenizer to go with the featureizer. And the features get passed into diet, into this diet classifier or the diet model, and then used to predict intents and entities. You can also tweak hyperparameters on the diet classifier. So in our experiments, we used 4 things. We used sparse features, we used glove, which is just a word-to-vec model, we used BERT, and we also used convert. Convert is a lightweight model that is trained specifically for conversations and on conversational data. I think it's Reddit data, and that's from Henderson and co-authors. It was released in 2019. So, if you want to take a look at the paper, I can share that with you, or you can just search for it. But yeah, Henderson and co-authors in 2019. So the data sets that we used to do our experiments for diet is called the NLU benchmark data set. The previous state-of-the-art on this data set was the Hermit NLU model that used Elmo and Elmo embeddings. So let's take a look at some of the results now that we saw with diet. The first thing we saw, that even with just the sparse features, right, diet outperforms the previous state-of-the-art. The previous state-of-the-art is Hermit NLU and Elmo embeddings, Elmo model. There was a lot of pre-training that went into that model, and diet outperforms that by nearly a point on the intent and entities without any pre-training models, just with counting the character n-grams. The second result that we saw here, which is also interesting, is with glove features, glove, which is a word-to-vec model. This outperformed BERT. So we used glove features, and they allowed diet to perform better than using BERT as a featureizer. And the third result that we saw was that convert embeddings performed the best on this NLU benchmark data set. Convert features have been available in Rasa actually for a while now, but now you can use convert featureizers with diet. And in our experiments, we found that it performed the best overall. And another super exciting result that we found is that not only does diet outperform BERT when using BERT as a featureizer, right, when glove worked better in that scenario, it actually outperforms fine-tuning the entire BERT model. So fine-tuning large-scale pre-trained models can be computationally very expensive and intensive, and it may not be as accessible to everyone. Another drawback with these large-scale pre-trained models is that they're very Anglo-centric. They're trained primarily on English and European languages, and we wanted to have a global representation. So that's another drawback with these large-scale pre-trained models. We saw that diet outperforms fine-tuning the whole BERT model. If you use diet with just sparse features and convert as the featureizer without any fine-tuning, it outperforms BERT. So when we looked at different data sets and featureizers that we use, like I said, there wasn't one pre-trained model or featureizer that was consistently best across our experiments. So feel free to play around with the model, try out different featureizers and models if you want. First, try it out with the default version that it comes with, and feel free to plug in anything that you find interesting. And we're very excited to see your results, or what you have to say, what your experiences are, and how we can sort of make this thing better together. So that's a little bit about diet and how we are now using diet for intent classification and entity extraction. And it is more accurate and better than everything that we've shipped so far. So we're really excited about it. And diet is open source, so feel free to check out the GitHub repo and give it a go and tell us what you think. Hopefully, if you like it, but if not, we want to know why. And if you find something that works better than this, please feel free to share. Okay, so now let's talk about the transformer embedding policy, which we published a few months ago. So the first piece of what we're trying to talk about is NLU, right? Which is extracting structured information from sentences and identifying the intents and entities. And the second part of it is selecting the next best action to take using the structured information, using this previous conversation history. So you can have rules that do this, of course, right? In the case of level 2 assistance, if the user asks about what Starbucks is, or if the user asks, is this, is my local restaurant open? You can probably check the time and say, yeah, it's open, and here are the hours, and that's very simple to do. But rules don't scale beyond a certain point, even though they might be super helpful to help you get started. So let's say, in addition to your spending history, where you wanted to check how much money you spent at Starbucks or something like that, your bot should also be able to tell you or perform a checkout for you in case you buy something. So in case you wanted to check out with an order that you have, it needs your address, it needs your credit card information, and if it doesn't have this information on file, right, it's going to try to gather this information in a form setting, and after it gathers this information, it's going to perform the checkout for you. So this is a typical happy path that can be described in code, and happy paths have already been solved. And there's a lot of software out there that makes happy paths even easier and better to do by just allowing you to, repurpose some things or templatize certain things or use starter packs and stuff like that. But, real user conversations don't follow the happy path. They often deviate from a linear or sequential path, and you can't predict user behavior. So users often interject with off-topic messages, or they loop back to earlier topics in the conversation, or they can digress by asking follow-up question. In this case, the assistant was ready to check out. It had the total, amount that this particular thing costed. It had the credit card information on file, and it said, hey, can I just charge the credit card that you used last time? And so all the user had to do here is to say, yep, go ahead. But they asked a follow-up question, which was, do I still have credit on my account from the refund that I got? So the main task here, which was to check out, has to be placed on hold. And now we have this sub-dialogue that we have to handle. And so you probably think that okay, fine, we'll keep a list of these. We'll keep a list of these sub-dialogues, and then we can check them off one by one, and then return to the main task at hand, which is a checkout. But what happens sometimes is that users will come back to this earlier topic. So you can say, you can handle that by keeping a check of it and say, yep, your account has $10 in credit. User said, okay, great. And then the user went back to asking about that and said, did you actually use my credit, right? So when users loop back to earlier topics, and when they engage in chit chat in the middle of a conversation, they, ask a joke, or they say things like, hey, are you a bot? They engage in small talk. You simply can't anticipate human behavior like this. So that's why it's super critical for you to test your assistant with real user conversations. And our recommended approach is that as soon as you build a minimum viable assistant that can handle most of these happy paths, test it with real users and add that training data and train with it, so your machine learning policies can better generalize from them and better predict how to handle unexpected user behavior, like what you see on my screen here. So an assistant whose purpose it is to automate conversations or handle a certain amount of customer service requests must be able to handle these types of conversations. And just using a state machine may not be best suited for this, as you can see, because they can't scale beyond if-else statements and rules. Let me just take a look at what's happening here. Okay. Yeah, Victor. So we'll come back to that question a little bit. You're right, it is a digression. Okay, So how do we handle this type of complexity and handle these types of multi-turn interactions in a model, right? So we worked on a way to attempt to solve this and build something that didn't have a state machine. We built a machine learning policy that could handle chit chat, interjections, nonlinear conversation, and digressions, like you mentioned, Victor, and unexpected user behavior. And the research team released the TED policy, which is a transformer embedding policy. But people, typically before we used transformers and attention-based policies or self-attention for this, people typically used recurrent neural networks to model dialogue. And that was, and it makes sense, right? Recurrent neural networks are not stateless. They have memory cells or a special memory effect, allowing information to persist. And as a result, you can keep track of context. So what you can do is you can have a stack of sub-dialogues like we talked about, have a checklist and say, all right, I have a checklist of talking about credit, so I'll get to that and keep adding these sub-dialogues onto this stack and check them off one by one. But if a user loops back to an earlier question in the checklist, you can have, you're gonna run into problems. So here we have a diagram, right? It's a very simple diagram. And we have a series of outputs. So the outputs are Y1, Y2, Y3. And the first output here which is just predictions that you want the model to make. And Y1, the prediction here is the question that it was supposed to ask, which is, can I charge the card that you used last time? The second, Y2, the prediction here is to listen for user input. The user said yes, right? So it just had to, the action there was to just listen. And the third action prediction that it had to take was to respond with something, which is, yep, you should have your order tomorrow, which is tracking an order. So what happens here, right, and the W's are just weights, and the input gets multiplied by a set of weights. So we apply another set of weights. We keep track of this middle state. We apply another set of weights before we get to the output. And so when we make a second prediction here, the memory, the middle state that's being tracked is transformed and added here. And the memory is evolved throughout the sequence, and this happens in a loop during the conversation. So the prediction at Y3 is dependent not just on the input down here, but it's also dependent on all of the previous inputs and the entire conversation history. So as a result, the model takes conversation history and context into consideration before it's able to predict the next action or response. And you'll find that this memory, this middle state here can be problematic, like we talked about, because it has to be updated each time there's an input. And the reason it does that is because it's operating on the assumption that everything in this conversation is important and everything in this conversation is meaningful. And that might not be the case for a goal-oriented system, or in a conversation where certain turns in a conversation, certain dialogue turns may not be that important or relevant to the outcome of the conversation or the goal at hand. And so in addition to that, obviously it can be super computationally expensive. So that brings us to the natural next step, which is, all right, so not all input should be treated equally. Not all input is equally important. You want to be able to pick which conversation turns to pay attention to and which conversation turns to ignore. For instance, if a user says, by the way, in the middle of all of this, tell me a joke, that digression there, that chit chat may not be as important of an input as the user saying something like, did you use my previous card on file, right? So in this example, which is from a Google blog post, is the connection between the word it and the words preceding it. And it uses attention, which has been a very useful concept in conversational AI, attention and self-attention. So in the first one, it says the animal didn't cross the street because it was too tired. And in the second one, it says the animal didn't cross the street because it was too wide. And the word it here refers to two different things, right? In the first one, it's the animal, and the animal didn't cross the street because the animal was too tired. And in the second one, it's the street. So the animal didn't cross the street because the street was too wide, right? And so that, as you can see, is pretty confusing even for just like when you and I are having a conversation. If I were to say something like that, I'm sure you would probably ask a follow-up question in some cases and say, you know, what is it referring to here? Did you mean the animal or the street? And here's a translation model again between English and French, and you can see how the model is paying different attention to different words in the input as it's producing these tokens. So some, as you can see, have a pretty like one-to-one correspondence, and then some are not so simple and have contributions from a lot of the previous pieces from the sentence. So transformer works with self-attention. So you're looking at the sequence to produce the next token. And that's what the TED policy does. The TED policy has a predefined architecture. So here, what you see here on this side is called a story. And if you've used Rasa before, that you'll know that this is how we define a conversation path. So switching context just a little bit from the previous use case where we were talking about Starbucks and making orders. Here in this example, actually, we should probably update this example, because this example, what it does is that it's a hotel check-in and a hotel finding, like a hotel booking assistant. So it asks you for details like the start date of your vacation, the end date, you know, how many people are going, and then maybe the price point, which of course, due to these crazy times that we are living in, a hotel doesn't make a lot of sense. So I should probably, that's good feedback for me, is that I can probably update this example, make it more relevant to, I don't know, ordering groceries or ordering food or something. But here, you know, this story here, this conversation path defines how the assistant can start to think about asking for these details, start, end date, location, price point, before searching for hotels and making a booking on behalf of the user, right? So that's what it should do. And as you can notice here, we are starting to see a whole lot of chit chat. And then the user is starting to be cooperative again and answer a question about the price point. And the user says, I want to look for, you know, expensive hotels, and it's for 4 people. Those slots, or the bot's memory here, is filled, and the bot goes on to search for hotels and then suggests a particular hotel. And then the user affirms it, you know, and the conversation ends there, right? So this graph that you see here is where we plotted attention. And as you can see, we are starting to pay attention here, right? We're using the previous user input, and we're tracking that, and we're paying attention to that. And here, as you can see, the model learned to stop paying attention to a whole lot of chit chat, because it realized that it wasn't very relevant to the goal at hand or relevant to the task at hand. You know, the model learns which conversation turns to pay attention to and which to ignore. And it ignored most of this chit chat history, and it started paying attention again down below, where the user was being a cooperative user again and answering questions. So you could add more chit chat to this model and more digressions and other, you know, ways a conversation could deviate, and the model will still learn to do this. It will still learn to pay attention in the beginning and not pay as much attention when you start adding chit chat and digressions and interjections, and then start paying attention again when the user is being cooperative. That's because it learns based on training data and based on, you know, self-attention mechanisms, what to pay attention to and what to ignore. So as a result, it's much more equipped to handle unexpected user behavior. With a recurrent neural network, each of these inputs gets tracked. Each of these inputs gets tracked and added, and it becomes harder to recover if our user were to cooperate again. But with the transformer embedding policy, it's able to recover, you know, very well. So this model, by the way, is open source, and it's available on GitHub, and I'm happy to share more information on it after the meetup via email or chat. You know, if I can send you some links, happy to do that. So essentially, the TED policy is a way to handle uncooperative user dialogues on fewer training data or fewer examples. So it uses these examples, and it's able to better generalize and better predict from these examples, looking at previous conversations, trains on them, generalizes so that when it sees something unexpected or sees something that it hasn't seen before, it is still able to make a reasonably confident prediction as to what should happen next, and based on that, what it can respond with. So no rules, but a whole lot of data and machine learning, you know, specifically self-attention to solve for sub-dialogues and multi-turn interactions. Okay, so we talked a little bit about the latest research for handling NLU, predicting intents and entities. And then we talked about the latest research, transformer embedding policies for dialogue, which is using data to be able to make a prediction as to what the response from the bot should be. So that essentially is how conversational AI, the way we think about it, works, right? So you have NLU and you have dialogue management. But that sometimes really isn't enough. NLP or NLU is not enough. You also need engineering best practices, because algorithms will only get you so far. You still need engineering practices like CI/CD and version control, and most importantly, you need lots of tools that allow you to get there faster. Whatever you use in a typical software development workflow to really scale conversational AI projects and go from POCs to production is something that you want to be thinking about if you want to build level 3 sophisticated assistants. So you want to still follow the best practices of CI/CD. You still want to write lots and lots of tests, because just because we're using machine learning policies and machine learning in general doesn't mean that it doesn't have to be tested. It absolutely does. Most of these things are not going to work until we write tests and really test it with real user conversations. So you still want to follow the 12-factor app methodology, make meaningful third-party integrations. So for instance, if your assistant was like a help desk assistant, and its purpose was to help you resolve routine technical issues, then it makes sense to integrate with like an incident management portal or something like ServiceNow, right? So really be thinking about what kinds of integrations you want to make to add skills or capabilities to your assistant, so it can actually not just answer questions, but do things on your behalf. Because it's great if you have an assistant that can answer your questions very well, handle unexpected user input, but if it doesn't actually do things for you, then it's not super useful. So what makes sense to add to your chatbot based on the purpose of your chatbot are things that you want to be thinking about. And we also sort of wanted to make the deployment aspect of it easier by abstracting away some of the complexity involved and doing something like this, and still where you can just run a script and it takes about 5 minutes, and you have a totally containerized deployment of Rasa open source and Rasa X. Rasa X is a tool set, which we can talk about in a little bit. It's also free. And what the script does is that it installs Kubernetes, installs a Helm chart with everything, just sort of abstracting away the complexity involved in deployment sometimes, which can be painful. Okay, so, machine learning and software best practices is still not enough. It's still not going to solve conversational AI. You also need training data, which I think most of you are either data scientists here or data engineers. You probably already know this better than I do. You need a whole lot of data so your model can learn from it and generalize from that data and be able to better predict an NLU output or better predict a response. So to train your intents and entities, you need training data in the form of examples. So different ways you can teach your assistant to recognize an intent. So if it's something like, I like food, then we want to give it different examples of food and different ways you can say you like food, right? This seems very easy here, I'll admit, and there are some intents that can be harder to hack and deal with. For instance, the concept of negation can be pretty difficult. You can say, I like apples, but if you don't like apples, the way that you express that is saying something like, I don't like apples, right? But there are other very complicated ways in negation could go. You could say something like, I would never eat apples, or that's the last thing I want, or something like that. So even large-scale pre-trained models use a simple heuristic with negation. They look at the word not, and everything that follows not is what you're trying to negate. So like, I do not like apples, then apples follows not, so that's what you're trying to negate. But if you said something like, I would never eat apples, or you'd really have to twist my arm if I were to eat apples, then that can be very challenging to do. But yeah, I know this looks simple, but either way, you need to give it like different examples for intents and entities. And the way that you give it training data for your dialogues or dialogue managements is the way that we recommend it is by adding stories or different ways a conversation path could go. You need happy paths, you need unhappy paths, and that's why it's super important to, as soon as you build an MVP assistant, just ship it and share it with like your colleagues, with people on your team, so they can start testing it. And you can really use those real user conversations to figure out how conversation paths can go, and use that as valuable training data so your models like TED policy can learn from it and generalize from it. And it's important that you make these continuous improvements and train on real user conversations using tools. And Rasa X is one of those tools, which is also free, which allows you to share your assistant with just, you know, it has a link that allows you to share your assistant, and you can share it with anyone. Let's say you're building a Slack assistant or a WhatsApp or Telegram assistant. You can't necessarily add everyone to your Slack workspace, but sometimes it can really be helpful if you wanted to just share them a link, and they can just click on that link, launch the assistant, talk to it. And using Rasa X, you can also filter conversations. You can also tag and annotate data, which can be useful when you're trying to train, you know, massive amounts of data. So Rasa X makes it easier for everybody, not just machine learning researchers, to be able to come up with a really robust and a really sound data set that you can use to either create a custom model or, you know, improve your existing models. And your data is still secure and proprietary, and it belongs with you and your assistant. Okay, so to recap, conversational AI is not easy at all, like we talked about. It's not solved, far from it. And our approach is that in order to build these really sophisticated assistants that can use machine learning and use the latest research out there to better predict intents and entities, and also better predict responses, you need really sound research, but you also need engineering best practices, and you really want to involve developers into your workflows, because, you know, the developer community has a great track record of shipping things to production, and so making this available in a flow that makes all makers to build and contribute to it is important for us. And you also need data so that machine learning models can better generalize from them and continue to get better. And you need powerful tools that allow you to make these continuous improvements. And so that's been our approach to this really exciting and interesting and challenging problem. We know that, you know, we're all sort of in this together and learning together. Yeah, it's an unsolved field, right? So we're all still learning. So I'd be happy to take any questions that you have now. And if you have any suggestions or better ways, if you want to share your experiences, if you have like better ways of doing things, I think that would be great to learn. Okay, cool. Thank you.
Thank you, Mady, again, for the wonderful talk. And thank you for joining us so early.
Yeah, no, of course.